Alright guys, this is our last topic, nuclear energy. And nuclear energy is when we are going to explore another one of Einstein's findings from 1905, which is the relationship between energy and mass. But the usefulness of the relationship is not the standard way it's traditionally written. It's actually in that there's great amounts of energy released whenever we could cause nuclei to change their mass by a little bit. And this is how that's going to actually happen. So we are going to actually become acquainted with what nuclear fission and fusion are, because both of these are ways of actually releasing energy that we could actually use to power our spinning magnets inside of our power plants that then generate all the electricity that we need in our homes and for our daily purposes. All right, and we also have to become familiar with this new idea of conservation of mass energy, and we will talk about what that means in a moment. So let's go back first to 1905, Einstein's year of miracles. I think it was called Annus Mirabilim. All right, and what Einstein ended up doing was applying special relativity to all of classical physics. He wanted to figure out what would all the classical physics equations be if you apply special relativity to make sure that all frames of references would measure the speed of light to be the same. And this is because most of Newtonian physics, right, requires quantities such as distance and time. And since distance and time are both big parts of special relativity, we'd have to actually come up with new mathematical models for momentum, new mathematical models for energy, right? And while actually exploring energy, he noticed something really interesting. The final total energy for any object he discovered would be K plus mc squared. And he called mc squared the energy an object has even when it is at rest. So ultimately, this begs the question of what is it? Like, what does rest energy mean and do? What's the meaning of it at the microscopic level and macroscopic level? So ultimately, what Einstein discovered was a form of internal energy, all right? The energy that comes from the fact that there are a lot of subatomic particles that are attracted to each other, especially subatomic particles in the nucleus, which is what rest energy is most directly related to, right? And this was a little bit of a strange notion because it opposed a very well-established concept. It opposed a whole notion of conservation of mass. So this is what we're going to need to do before we could actually go and continue the experimentation of looking at how Einstein's idea dukes it out with conservation of mass. We have to first make sure we can measure really, really tiny amounts of mass. We're talking about the masses of a single nucleus. So the way we're going to do this is we're going to invent a new unit for mass, just like how we invented a new unit for energy called the electron volt. So the new unit for mass is basically going to be the mass of one proton. All right, and scientists found this by taking the total mass of a carbon atom and dividing it by 12, because they know that there are 6 protons, 6 neutrons inside the nucleus of a carbon, and there are also 6 electrons that have negligibly small mass. So if you divide by 12, you will basically find the mass of a single proton. All right, so one atomic mass unit, sometimes also referred to as 1 U, so without the AM part. So one atomic mass unit is equal to 1.6 times 10 to the negative 27 kilograms, all right? So you should be able to actually answer these questions. Why don't you pause and see if you understand how to do the unit conversions? Now, if you paused, the answer to these questions is that the mass of a neutron is 1 atomic mass unit, right? Because a neutron and proton are about the same mass, right? The mass of a proton is 1 atomic mass unit. All right, the mass of a 2 kilogram block in atomic mass units, well, the way we would do that is through some unit conversions. If you take a look at the whiteboard, all right, so we know 2 kilograms is what we're trying to convert. We want to multiply it by our conversion ratio. We want to convert from kilograms to atomic mass units, all right? And the more common way of writing atomic mass unit is U by itself. All right. So what is the relationship between kilograms and atomic mass units? Well, we said so earlier. It was 1.6 times 10 to the 10 to the negative 27. All right, kilograms. And then this would be 1 atomic mass unit. The kilograms will cancel out. So we could find out that our final answer over here is going to be, I think I wrote it down earlier. It's going to be 1.2 times 10 to the negative 27 atomic mass units. All right. So once again, this is how you could do unit conversions if you needed to practice setting up a ratio. Once again, we could use this ratio in a variety of ways. So let's say if we wanted to go from atomic mass units to kilograms, all right, that would be the next problem, the problem that you see right over here. All right, so what about 1,000 protons? How many kilograms would 1,000 protons be? So 1,000 protons, all right. I guess I'm gonna try doing it down here. Let's hope it fits. So 1,000 protons is 1,000 atomic mass units. All right, we're gonna multiply it by our ratio. You could set up a ratio as a fraction, and we know our goal is to get kilograms. So we want atomic mass units on the bottom, kilograms on the top. The ratio of atomic mass units to kilograms was 1 atomic mass unit is 1.6 times 10 to the negative 27 kilograms. All right, so our final answer over here, we can see atomic mass units cancel out. So we are basically going to have a final answer of 1.6 times 10 to the negative 24. All right, kilograms. So let's check if our answers make sense. That is the most important thing to do when you're converting between big units like joules to tiny units like electron volts, or big units like kilograms to tiny units like atomic mass units. So in order to do this, let's actually take a brief look. We said 2 kilograms would be, and I could actually find an error with my work right over here. Perfect example of exactly why you need to double check. All right, 2 kilogram block, all right, in atomic mass units. I wrote it was 1.2 times 10 to the negative 27. Should a 2 kilogram block have such a tiny amount of mass? No. This negative was a mistake because I saw the negative 27 here and I just repeated it in my answer. But it should be a big number, 1.2 times 10 to the 27th, which would make a lot of sense. 2 kilograms is a lot of mass, so therefore it should be a lot of atomic mass units, right? A lot of these protons inside of 2 kilograms. Meanwhile, 1,000 protons should be a really tiny amount of kilograms. It should not be a lot of mass, right? Because a kilogram is a lot of matter, and the mass of particles is actually significantly smaller. So this is how you could once again double check your work. And let's continue on. So this, as our techniques for measuring mass actually became more precise, we actually started noticing that the atomic masses of uranium and its decay products were different. We could actually measure the total mass and notice that if we measure precise enough, measure to say the 6th significant digit, we'll actually notice a pretty big decrease in the mass. All right, so why is it a pretty big decrease? It's because technically, so 1 mole of that material, which is going to be the certain number of measurable grams, right, would have an Avogadro's worth of particles. All right, so we're talking about a huge amount of energy release, where Avogadro's number, I don't remember it off the top of my head, but Avogadro's number is what, 10 to the 23rd. So we are going to end up taking this, whatever energy is released from this change in mass, and multiplying it by 10 to the 23rd. All right, so and that's exactly what they found out. They wanted to figure out what was happening to this missing mass of 0.0057 atomic units, and they found out it's released in the form of molecular kinetic energy or thermal energy. So we have to then redefine the conservation of mass to become the conservation of mass energy. So here's the thing next. We want to start calculating how much energy is actually being released from this change in mass. And this is why, once again, Einstein's rest energy equation of E equals mc squared is not going to be as helpful for us. We already know that the energy being released is going to be released in the form of kinetic energy, or in the form of photons, right? So we just want to know how much energy is being released. So all we have to really look at is change in mass. So then, in order to do this, though, we have to be very, very careful about our units. We have to make sure that our units are all, our units and our constants are being measured in the right comparable units. So for example, if you use kilograms, you're going to get joules, or if you use atomic mass units, a lot of the conversion numbers we're about to go into will get you electron volts, all right? So this is what I mean. When you look right over here, you could see 1 atomic mass unit is equal to 1.6 times 10 to the negative 27 kilograms. But you'll also see this interesting conversion factor of mega electron volts, all right? 10 to the 6, that's what mega stands for, 10 to the 6 electron volts, and it's 931 times 10 to the 6 divided by c squared. So what does this even mean? So let's take this slowly. 1 atomic mass unit is equal to 931 mega electron volts divided by c squared. We're going to actually break this down, and what we know is that 1 atomic unit is 1 nucleon, so this much mass, 1.6 times 10 to the negative 27. Let's look at how much energy is released if we change exactly 1 nucleon worth of mass. So we're going to do this in standard units. The change in energy is going to equal to the decrease in mass by this many kilograms times 3 times 10 to the 8th meter per second squared. This is a total of 1.5 times 10 to the negative 10 joules. So let's now convert this into electron volts, all right? And then later on, mega electron volts. So 1.5 times 10 to the negative 10 joules is going to be equal to 9.31 times 10 to the 8th electron volts, or 9.31 times 10 to the 2nd mega electron volts, right? If you think about 9.31 times 10 to the 2nd, that's the same thing as 931 mega electron volts. That's where the 931 mega electron volts is coming from. It's how much energy is being released if we convert 1 atomic mass unit worth of matter, right? So now I'm going to actually switch to my whiteboard. Maybe that was too fast for you. If you needed a little bit of assistance with that, I'm going to show you unit conversions right here. Feel free to skip using the chapter functions if you feel very, very comfortable with your electron volt conversions. If not, I'm going to walk you through it one time, okay? So if we actually take a look, we want to convert from joules to mega electron volts. So I'm going to just round my numbers a little bit right now, all right? Which I guess we can't do, because realistically we are talking about needing a lot of significant figures if we're ever really going to talk about nuclear physics. So I will keep it as 1.491 times 10 to the negative 10 joules. All right, so we know that a joule to electron volt, we're just going to have to multiply this by our next ratio. Our next ratio is joules to electron volts, all right? So we have 1 electron volt is going to be 1.6 times 10 to the negative 19 joules. I believe that is correct. I'm going to double check for myself one time before continuing, all right? So on our AP equation sheet, all right, so yep, the conversion factor is in fact correct, and it makes sense because once again, the joules, 1 electron volt should be a really tiny number of joules of energy. All right, so this does bring us to our next value. So now we know how many electron volts we have, which I believe is 9.31 times 10 to the 8th electron volts. All right, so to convert this to mega electron volts, once again, you could do a conversion factor of electron volts to mega electron volts. Well, 1 mega electron volt should be a lot of electron volts. How many? I believe is 10 to the 5th. 10 to the 6th? 10 to the 10 to the 6th. Ooh, okay, I'm definitely starting to feel a little bit tired. But over here, you could see that this then becomes 9.31 times 10 to the 6 mega electron volts. All right. Sorry, not 6. What am I doing? All right. Over here, 10 to the 2nd. All right. And what does that mean? I'm going to write this in full scientific notation right now. That means we're multiplying by 10 2 times. So we could see that's where they get 931 mega electron volts. All right. So there you go. That is how we found this conversion ratio of mega electron volts released per 1 atomic mass unit. Okay. So now let's return back to our scene. All right. So we now know what this number means, all right? So this is, all right, so this is the total energy released if we convert 1 atomic mass unit into energy, where C is just 3 times 10 to the 8th meters per second. So now that we know the ratio, we can set up a few things, all right? We could actually set up a unit of mass. Take a look. 1 atomic mass unit should equal energy divided by c squared. All right. So this energy divided by c squared is actually a unit of mass. This is just saying that we know that this mass is already going to release 931 mega electron volts. So what we could do is, if we actually have this, if this is a unit of mass, multiply it by c squared, and you'll find out exactly how much energy is released. We'll go into this more in a moment. The other useful ratio we found out is that c squared technically is equal to 931 mega electron volts for every 1 atomic mass unit. All right. So let's actually apply this in practice example 1 for using the c squared as a mega electron volts per 1 atomic mass unit versus another practice problem where we will just be given the mass in mega electron volts per c squared. All right, so I will show you both how that works in these upcoming problems. So practice problem number 1, how much energy did we actually release in the uranium alpha decay? So to figure that out, we could just take the energy release equation, find out the energy released is equal to this much change in mass, multiply it by c squared, which we found out was 931 mega electron volts per 1 atomic mass unit, and then the atomic mass units cancel out and show us that it is just going to be 5.931 mega electron volts in total. All right, so this is just using the c squared ratio. Once again, if you're a little bit confused about where the c squared ratio came from, you could check out my whiteboard right here. I will solve it one time. So the c squared ratio, if we take a look, all right, change in energy equals change in mass times c squared. If we move the change in mass across, we could just see the c squared value is going to be the total change in energy for that 1 unit of change in mass. And that's where we found out the c squared is actually equal to, when we change 1 atomic mass unit into 931 mega electron volts. All right. That is how we actually figured out the c squared value. So it's not on your equation sheet, but if you'd like to write it there to help you remember, feel free to use it. It's actually pretty helpful. All right. Then practice problem number 2. What if we're already given mega electron volts over c squared as a unit of mass? So why is mega electron volt over c squared a unit of mass? I guess now's a good time for me to show you that as well. All right. So if we take a look over here, this is actually more relating to Einstein's rest energy equation. So we want to actually figure out what is a unit of mass. A unit of mass here is going to actually be the total rest energy divided by c squared, all right? So mass is going to be measured in atomic mass units, and therefore it's going to be equivalent to if we have mega electron volts divided by c squared, all right? So how do we use this? This means an atomic mass unit is equal to this same unit. You just on the left, but I think seeing an application is going to help. So let's take a look over here. What is the rest energy? What is the rest energy of nitrogen? All right. So over here, if we actually take a look, we have a table giving us the mass measured in mega electron volts over c squared. So this is the mega electron volt values. So how do we actually figure out the total rest energy of nitrogen? So how much energy the nitrogen has on its own, not via energy conversion. All right, and in order to do that, we would have to take the mass and multiply it by c squared, because rest energy, E equals mc squared. So if we take a look at the nitrogen right over here, we are just trying to calculate not the change in energy, but we're just trying to calculate the total energy of the system. This is like in the past, where in our energy bar chart, we'd look at types of energies in the beginning and types of energy at the end, and we just want the total amount of energy it has in one of these moments in time. All right, so for right now, I'm just going to help us calculate this rest energy. So they said nitrogen has a mass of 113,043.15 mega electron volts over c squared. If we want to find E rest is going to equal this mass of 1,343.15 mega electron volts over c squared. And then, of course, this mass has to be multiplied by c squared. The c squareds cancel out, and we find out that the rest energy is just equal to the amount already provided. So the main difference is trying to identify if you're working with rest energy or are you working with energy release. All right, so if you take a look, that's exactly what I showed here. So let's actually move on to practice problem number 2 continued. So in order to actually solve this problem, why don't you guys pause it if you'd like to figure it out. This problem has a few steps. All right, so if you paused and attempted it, the next slide actually shows you the answer over here. All right, so your goal was not just to find the total amount of energy released. Your goal was to find the frequency of the gamma rays that are being released. So in order to figure that out, you had to add up the total rest energies in the beginning, the rest energy of nitrogen, subtract them, and that would give you the total mega of electron volts of energy of released. Then the gamma radiation, so if you take a look here, starting rest energy of both of these in the beginning, the gamma energy is the energy released, and this is the rest energy of nitrogen, all right? So if we take a look, we could actually see how I believe I solved this not using the rest energy equation itself. I decided to solve this last year using the change in mass equation. So we found out the total change in mass was 7.67, and then I decided to multiply that by c squared to find out that the total energy of the photon, or the energy released, must have been 7.67 mega electron volts, and then I set that equal to the energy of my photon to find out that the frequency of the gamma radiation would be approximately about 10 to the 21 hertz, and that brought us to answer choice D. So to summarize nuclear energy, you should be able to calculate the total energy released in any nuclear reaction using the atomic masses of those elements. You should be able to use energy conservation to figure out how much photon energy is actually being released, and you should be able to determine properties of frequency or wavelength using Einstein's photon equation. So, all right, fun facts, which is just how to make sense of nuclear energy. So at this point, if you'd like to actually stop, you may. I'm just going to walk you through a few final fun facts before we actually conclude our modern physics unit. So a few things that you should actually bear in mind is that nuclear energy is actually about the stability of atoms, and scientists have actually tried to find the stability of all the different nuclei, all the way from uranium to hydrogen and helium. All right, and here's the interesting thing that they found. The more negative the electric potential energy of an attractive interaction is, the more stable that system would be. So the cool thing that we found out is that iron is actually one of the most stable elements in our observed universe so far. And as you look, if we do fission, if we take uranium, all right, uranium is not as stable, so it's not as a low of an energy as iron. So if we take uranium and let it fission and break up into a more stable particle like iron, we're going to release energy. All right, and this is actually how our nuclear power plants are working. They actually just keep breaking up they break up these radioactive, very, very unstable large nuclei into something more stable, and that release in energy is how we actually get our thermal energy for the nuclear reactions. Meanwhile, our sun takes hydrogen. Take a look at hydrogen over here, right? This is actually very, very low amounts of, this is very, very, high. Let me pause for a moment. This is a attractive situation in the nuclei that, if fused into helium, would cause also a release in energy, and that release in energy is actually going to be much larger than taking uranium and turning it into iron. All right, so taking things like hydrogen and turning it into helium would also cause a release in energy. And this is actually one of the next goals in engineering. We want to see if we could create a fusion energy source. We already use a fusion energy source on an everyday basis, and that would be our sun. Our sun is essentially a giant, big pressure cooker that takes all of the particles and just keeps fusing them, and that's why we believe the center of a lot of planets or suns might actually be consisting of a iron core. All right. So to this very day, we could see that we're using a lot of Einstein's ideas from 1905, and we've tested it in multiple ways, and we have yet to actually find any big breaks from his current ideas. So the cool thing to look at the very end of this video is where we are in terms of physics. We've actually explored all of classical physics at this point, minus chaos theory. All right. We have also started looking at some of Einstein's ideas of special relativity, although we haven't looked at space-time and general relativity yet. And then in terms of quantum physics, we haven't looked at quantum information, but you do now know nuclear theory, atomic theory, and a little bit about the standard model using conservation in order to figure out the fundamental particles of the world. And then finally, there was also the talk about the three interpretations of quantum physics, which is actually a little bit of philosophy, and then we are still trying to figure out all this information about the world. So the future of trying to make Einstein's relativity ideas fit with Einstein's general relativity ideas of space-time fit with quantum theory is what some people are working on, called quantum gravity, and we're also observing a lot of things about the universe that we can't explain, including turbulence of water. So guys, that is the end of AP Physics 2. I hope you guys enjoyed the journey of learning all these ideas, and I will see you guys for some AP review.